Lesson 30 deals with graphs of quadratic functions. And let's see here. Okay, sorry for the delay. Lesson 30 deals with graphs and also further applications of quadratic functions. Now, we know that a quadratic function normally has a standard form of ax squared plus or minus bx plus or minus c. Well, there is another form that we'll talk about a little bit later. F of x is equal to a times, in parentheses, x minus h squared plus some k. Both of these types of quadratic functions are known as parabolas. Now, regardless of which form, a tells us exactly what the graph should look like. And a parabola is a curved function. If a is less than 0 or negative, then your parabola is opening upside down, like an upside down cup. And the top point is known as the maximum point. However, if a is positive or greater than 0, then our parabola looks like a regular cup, and the point at the bottom of the cup is known as a minimum value. Now, both points, regardless of whether the point is at the top of the curve or at the bottom of the parabola, that is known as a vertex. And the vertex is normally the ordered pair, whatever h is and whatever k is. And we'll see how to identify the vertex, again, regardless of the form of our quadratic function. Now, a couple of items of interest. In my math lab, you will be asked to find certain things. The first thing is the domain of the parabola. Well, the domain for a vertical parabola is always real numbers. We know that the domain is what the x value or the x coordinate can be. And you can plug in anything that you want to for x and get a real number for f of x or y. So the domain is always all real numbers, or interval notation from negative infinity to positive infinity. The next thing you'll have to find is something called the axis of symmetry. The axis of symmetry is a vertical dotted line that cuts our parabola in half. And the axis of symmetry tells us that both halves of the parabola are mirror images of each other. And to find the axis of symmetry, you express it as an equation, x equal to whatever h is from your vertex. The next thing you'll be asked to find is the range. And the range is what the y values can be. So the range is usually whatever the y values can be, and the range can be found a little easier after you've graphed the parabola. So we'll hold off and discuss the range a little bit more later. Let's look at a parabola that we need to not only graph, but also find its characteristics. Given the function f of x equal to x squared minus 3, we need to give the vertex, the domain, the axis of symmetry, the range, and also graph this particular vertex. Well, graph the vertex, plot the vertex, and get the graph of the parabola. Now, our parabola is not in the x minus h squared form, but we can rewrite it as such so we can identify the vertex. So we can actually rewrite this as x minus 0 squared minus 3. Now a is still the leading number in front of your x. So in this case it's understood to be 1. Now because a is positive, that means our parabola will be a regular shaped cup, opening upward. The vertex is h, which in this case is 0, and k is just the number outside the parentheses, including its sign, so that would be negative 3. So there's our vertex. The domain, you can plug in anything that you want to for x and get a real number for y, or f of x. So the domain is all real numbers. Or in interval notation, from negative infinity parentheses to positive infinity. Next, the axis of symmetry is the equation x equal to h. In this case, h is 0. So your axis of symmetry is the equation x equal to 0. And we will find the range after we graph the parabola. Now, to find a couple more points, just draw your xy table. And I'll pick one point to the left of our vertex. Let's say x equal to negative 1. And let's pick a point to the right of the vertex. Let's say 2. Or you could use positive 1. That would be suitable. And we just plug these values in place of x to get the corresponding y values. So when we plug in negative 1 for x, we get negative 1 squared minus 3, which is negative 1 squared is a positive 1. Minus 3 gives us negative 2 for y. If we let x equal to positive 1, Then we have 1 squared minus 3, which also garners negative 2 for y. So let's plot these other 2 points. And connect the dots. And my graph is off slightly, but in my math lab, when you use the graphing tool, the quadratic or parabola tool, your graph will be more exact than mine. Let's look at another parabola that we need to not only graph. Oh, before we look at the next example, we need to find the range. The range is where the y values start and where they end. So the y value starts here at negative 3 with brackets, and the graph keeps shooting up toward positive infinity. So that's your range for this particular parabola. Let's look at another parabola in which we need to graph and find all of its characteristics. Okay, the next parabola we have f of x equal to, in parentheses, there's a negative 1 on the outside, sorry, times, in parentheses, x plus 1 quantity squared minus 2. And we need to find all of the characteristics of this parabola and graph the parabola as well. First, let's identify A because it tells us exactly the type of graph we should get. Because A is negative, then that means our parabola, when we graph it, should open down or up. It's an upside down cup. Now, to find the vertex, you just think opposite signs for inside the parentheses only. The opposite of a positive 1 is a negative 1. So that's your H. And the opposite, well, we don't need to do opposites for K. Whatever K is, whatever the number is on the outside, including its sign, that's K. So this will be negative 2 for K. Next, the domain is still all real numbers because you can plug anything you want to in place of x and get a real number for y or f of x. So the domain is still all real numbers, or from negative infinity to positive infinity. Next up, the axis of symmetry. Again, you write that as an equation, x equal to h, and h is negative 1. So our axis of symmetry is the equation x equal to negative 1. And we'll find the range after we graph the parabola. We can go ahead, however, and plot our vertex. Now, if you're graphing by hand, all you need is one point to the left of your vertex and 1 point to the right of your vertex. So let's draw our XY table. And I'll choose -2 and 0. And plug those values in place of X to give the corresponding Y values. So we plug in -2 first. And that gives us -1 squared. -1 squared is a positive 1. But times that -1 will give us a -1 minus 2. So our first Y coordinate is +3. Now let's plug in 0 for X. So we have -1 times, in parentheses, 0 plus 1 squared minus 2. And working inside the parentheses, that gives us 1 squared. And 1 squared is a positive 1. Times that -1 still gives us -1. And then minus 2 will still give us, that should be a -3 for both, sorry. So each Y coordinate would be -3 instead of +3. Now let's plot our other 2 points and draw the graph and also find the range. So -2, -3 and 0, -3. And as the value of A predicted for us earlier, our parabola will be upside down. Now, from the graph, we can determine our range. It's coming from negative forever, and it's stopping at the Y value -2. So our range is parentheses -infinity, comma, -2 brackets. Let's look at one more example in which you have to graph a quadratic function and find all of its characteristics. So y'all give me just a second. And we'll look at the next quadratic function. We can actually, regardless of the type of parabola we're about to go over, vertical parabola, our domain is still -infinity to +infinity. So let's look at this next parabola. It's in the form x minus h squared plus or minus k. So from here we can easily identify the vertex. To find h, all you do is look in the parentheses and ask yourself, what is the opposite of our given number? So the opposite of negative 2 is positive 2. So that's our h. And for k, you don't do opposites. Whatever number is on the outside of the parentheses, including its given sign, then that is k. So k is positive 1. And let's go ahead and plot our vertex. Now, how we know that our parabola will open up just like a regular cup, and by the way, this is also known as concave up if it's just going upward. Our number understood to be in front of the x is 1, and that happens to be the value of a. And because a is positive, then that means our parabola is concave up. Now, if a was negative, then our parabola would be upside down. It's like if you take a cup and turn it upside down. That's known as being concave down. Next up, the axis of symmetry is the equation x equal to h, or x equal to positive 2. And again, we'll find the range after we graphed our parabola. Now we need 1 point to the left of the vertex and one more point to the right. In my math lab, you may just need one additional point besides the vertex. But since we're doing this by hand, let's pick 2 additional points. Let's use positive 1 and positive 3. So when we plug these values in place of the x, when x is equal to 1, we have negative 1 squared plus 1. And negative 1 squared is a positive 1. Plus 1 will give us a positive 2 for y. And when we plug in 3 for x, inside the parentheses, 3 minus 2 gives us a positive 1. And we're squaring it. And when we do the proper order of operations, we still end up with positive 2 for y. So just like that, we got 2 quick and easy points to go along with the vertex. So let's plot our 2 points. And just connect the dots to draw our graph. Again, in my math lab, your graph will be more exact. Now, based off the graph of our parabola, we can find the range. And remember, the range is where your y values start and end. So right here at the vertex, the range starts at the y value positive 1. And the graph keeps going upward toward infinity. So the range is from 1 brackets to positive infinity parentheses. Now, if your parabola is in this form, f of x is equal to a times, in parentheses, x minus 8 squared plus or minus k, then it's fairly easy to find the vertex. But what if your parabola was in this first form? Instead of completing the square, there is a simple formula you can use to find the x-coordinate of your vertex. So let me introduce that formula to y'all. And you use this formula if your quadratic equation is in this usual standard form. And the formula is x is equal to negative b all over 2 times a. You identify a and b the same way you would if you were using the quadratic formula. Let's look at this first parabola. We have f of x equal to x squared plus 2x minus 8. And we're not graphing this function. All we need to find is the vertex. To find the vertex with a quadratic equation in standard form, use the formula x is equal to negative b all over 2a. For this function, b is positive 2, and a is understood to be 1. So we have negative 2 all over 2 times 1. And technically, I put x, but we're really finding the h value of our vertex, the first coordinate. Now, to find the second part of your vertex, namely k, all you do is everywhere you see an x in your original function, plug in negative 1. So negative 1 squared is a positive 1. A positive 2 times negative 1 will give us negative 2. And when we combine everything with negative 8, we get negative 9 for k. So our vertex is the order pair negative 1 and negative 9. Again, you don't have to complete the square or use any other type of method. This handy formula will help you find the vertex. Let's look at another function. And this function is also in our standard form. And we need to find just the vertex only. So we have the given function f of x equal to 3x squared minus 2x plus 8. Again, a quadratic function in standard form, we can use our shortcut formula. H or x, same deal, is equal to negative b all over 2 times a, in which a is positive 3 and b is negative 2. So we have all the information necessary to find the first coordinate of our vertex. Now in the formula, b is negative, and our b is also negative. So we got a double negative up top, and denominator 2 times 3. A double negative will change to a positive 2 all over 6, and that reduces to 1/3. Now we need to go back and find the k portion of our vertex, and to find k you just take 1/3 and plug it into every x into your function. So we have 3 times 1/3 quantity squared minus 2 times 1/3 plus 8. Now 1/3 squared is 1/3 times itself, so that will give us 1/9. Now we can simplify the 3 into 9. 3 can go into 9 3 times. So we have here 1/3 minus 2/3 plus 8. We can combine the fractions because they have the same common denominator. So that would be negative 1/3. And I'm going to make it easier to combine, I'm going to rewrite the 8 as 24/3. I did that so it will make it easier to combine the number with the fraction. So k is 23/3. And our vertex as an ordered pair is 1/3 and 23/3. This concludes lesson 30. Next up, we will cover lesson 31 on exponential functions. Lesson 31 deals with something called an exponential function. And the title says exactly the type of function that we will be dealing with. You will have a function that's being with a base that's being raised to some type of power, whether it's a positive or negative exponent. So that's the general form here. And let's look at this first function that we need to graph. How to graph this function: you draw your XY table, and since we're doing this by hand, pick 0, that's a good choice. A negative number, let's say -2, and let's pick a positive 2. First up, replace that exponent of x with -2. Now, the negative exponent means reciprocal. So the reciprocal or flip of 2 to the -2 is the same thing as 1/2 squared. And to graph this point accurately, we'll change 1 over 4 to its decimal equivalent, 0.25. So negative 2 and 1/4 is roughly right about here. Now, if we let x equal to 0, we have 2 to the 0 power. And any positive or negative number, negative integer to the 0 power is automatically 1. So we have the order pair 0, 1 that we can plot. And finally, when we let x equal to positive 2, we have 2 squared, which is just positive 4. Now, if you pick a few more values to plug in, if you plug in 3, that would be 2 to the 3rd power or equal to 8. So with each increasing number, your y's are going to increase also, each positive number. So this is how your graph will look. And the tail will never ever cross the x-axis or go below 0 in this case. Because if you pick anything less than negative 2, like say negative 3, that would be 2 to the negative 3rd power, or 1 over 2 cubed, which is 1/8. And that's even, it's not quite 0, but it's definitely smaller than 1/4. Now, what goes along with exponential functions is something called a logarithmic function. And an exponential function and a logarithmic function, they are usually inverses of each other. So let's discuss how to graph a logarithmic function. Before we talk about how to graph a logarithmic function, we need to discuss how to convert something from a log form to exponential form. So if you have something like y equal to log base b of, let's say, x, then in exponential notation, your b is your base, and it's being raised to the y power, and that's equal to the given function, in this case just x. So if you have to graph something by hand, and graph a log function by hand, convert it to exponential form, and then you can easily find points to plug in. So let's look at this log example. We need to graph y equal to log base 3 of x. Well, in order to graph this by hand, we need to change the log function, convert it to exponential form. So our base is 3. Our exponent is y, and that's equal to just x. Now we can, this time around, find points to plug in for y to get each x value. And I'll just pick a negative number, 0, and let's say a positive number. Now, when we plug -1 in place of y, that would be 3 to the -1 power, or just 1/3. And we know that is 0.3 repeating. So when x is 0.33, which is just shy, a little bit greater than 1, greater than 0, this will be kind of right here almost. Now, if we let y equal 0, 3 to the 0 power is 1. So we have the order pair 1, 0 to plot. And finally, if we plug in 1 for y, that will give us 3 to the first power, or just 3 for x. Now, if you plug in something greater than 1, then it will go off the Cartesian plane, but it'll keep going up a little bit. Again, this is just a rough sketch. But this is what your logarithmic function will look like graphed. Let's look at another exponential function and also another another logarithmic function. Let's look at another log function first. We need to graph the log function y equal to log base 2 of x. To graph this by hand, we need to convert our log function into exponential notation. So our base is 2, our exponent is y, and that's equal to the function x. Now we can draw our xy table. And this time around, we are choosing values to plug in for y. Let's say -2, -1, 0, 1, and 2. I chose 5 points this time so we can get an accurate picture of our graph. So if we let y equal to -2, then that gives us 2 to the -2 power. And we saw earlier that was 1/4 or 0.25. So 0.25 and -2 is roughly right here. If we plug in -1 for y, 2 to the -1 power is 1/2, and that's 0.5. So 0.5 and -1 is just a little bit more than our previous point. If we let y equal 0, then 2 to the 0 power is 1. If we let y equal to +1, that's 2 to the first power, or just 2. And finally, if we let y equal to 2, we have 2 squared, or 4 for x. And our log graph looks similar to the previous one. So here's the graph of this one. Going back to exponential functions, another thing we can do is if we have an exponential equation that we need to solve for a particular letter. So let's go over some examples on how to solve, and this is still lesson 31, solve exponential equations. Our first equation, we have 8 to the x power equal to positive 16. If possible, try and get each base to be the same base. So 8 is base 2, or 2 to the third power. So we can rewrite 8 as 2 to the third power and bring down that x. And 16, we can also write that in base 2 form. 2 to the fourth power is 16. Now, in this section, once you get the same base, you can set the exponents. There's a rule with exponential equations is if the bases are the same, then that means the exponents must be the same or equal. So you set the exponents equal to each other and solve for x. So when we divide both sides by 3, x is equal to a positive 4/3. Let's look at another exponential equation to solve. We have an example 2, 3 to the 2x minus 1 power equal to 27 raised to the x plus 4 power. On the left side, the base 3 is already in simplest form. So let's get the right base, the right-hand side base, 27. Let's rewrite it also as base 3. So we know 27 is 3 to the third power. Now, because the bases are equal, then that means the exponents are equal. So bring down the exponents. We have 2x minus 1 equal to, and on the right-hand side, let's go ahead and distribute that 3 in the exponent. That will give us 3x plus 12. Now, we can solve for x. Subtract 2x from both sides. And you can also, in the same step, subtract 12 from both sides. So when we perform those transformations or moves, we end up with negative 13 equal to x. Let's look at another example. We have the equation 3 to the x power equal to 1 over 9. And we need to solve for x. The left side base is already in simplest form, so let's focus on the right-hand side. That 9, we can rewrite it as 3 squared. Now, we don't have the same base just yet because that 3 on the right-hand side is in the denominator. We can rewrite the right-hand side from a positive exponent to a negative exponent. So we have 3 to the x power equal to 3 to the negative 2 power. Now, because the bases are the same, we can now set the exponents equal to one another. So our final answer, we didn't have to really solve anything here, is x equal to negative 2. So this is how you would solve exponential equations. Get the bases to be the same so you can set the exponents equal to each other. Earlier we discussed logarithmic functions, and you will be given some logarithmic equations that you have to solve. Just like we did when we had to graph a log function, anytime you're given a logarithmic equation, you have to convert it into exponential form in order to solve. Now, one restriction about logs, a log has to be greater than 0. Keep in mind, our general form for log equations, is y equal to log base b of x. And to convert that from a log form to exponential equation or exponential form, the b is the base, y is your exponent, and that's equal to your function x. So let's look at a logarithmic equation we need to solve. We have log base 5 of, in parentheses, 3x plus 2 equal to positive 3. And we need to solve for x. Step 1, convert your log equation into an exponential equation. So our given base is 5, and the exponent is usually off by itself on the other side, so that's 3. And that's equal to our function 3x plus 2. Five cubed is 5 times 5 times 5, or just 125. And you're left with a basic linear equation to solve. So subtract 2 from both sides, and that gives us 3x equal to 123. And the last step, divide both sides by 3. and that gives us positive 41 for our answer. Another stipulation is, I believe your base has to be positive in order to solve a log equation. Let's look at another log equation that we have to solve for. Solve for x again. We have log base 7 of the function 8x minus 9, and that's equal to 2. Again, to solve a logarithmic equation, you must convert it to an exponential equation. So our base is 7, and the exponent is 2. And we set that equal to our given function, 8x minus 9. At this point, square the 7, that makes 49. And again, you have a regular equation to solve. Let's add 9 to both sides first. So we have 8x equal to 58. And the last step, next to the last step, divide both sides by 8. And reduce your fraction to lowest terms by dividing both numbers by 2. So our final answer is 29 over 4. Just like with radical equations or square or exponent equations involving an exponent, we need to check our answer. And to check your answer, you plug it into your original equation. Replacing x with 29 over 4 minus 9, and we're checking to see if this whole thing is equal to 2. So inside the parentheses, 4 can go into 8 2 times. 29 times 2 is 58. Minus 9, that gives you 49. And when you convert this from a log to exponential notation, your base is 7, your exponent is 2, and that's equal to 49. So that is true. So our answer is correct. This concludes Lesson 31 and also part of Lesson 32.
Your meeting has ended.